Okay, we are going to discuss programmable logic controllers. Programmable logic controllers are basically programmable, and they are digital instruments. They're like computers, basically, and then they are what we use them to control what call this in automation, basically, to control our different gadgets. Yes, they are sometimes called PCs, PCs as in programmable controller, but then now because of the conflict with the personal computer, we choose not to call them that. What we then do is when you look at them, what do you expect to find on a basic PLC? You expect to find an LCD display, liquid crystal display. Why? So that you can see, you can diagnose, you can look at your program, you can check for errors in the event of malfunctions and stuff. So we need that screen to be able to read our programs and then to be able to we know what displays are for. So when you have a program, sometimes we want to see what's going on, and therefore we need this display. But some of the PLCs, they don't have a display. You rather use get a display as a peripheral device, a plug-in. Some of them, most of them would use a laptop, not a laptop as such, a PC, right? You get used to your own, then you think, no, sometimes it's just PCs that we use to display whatever we want to see. Alright, also you expect PLCs to be packaged with internal timers, counters, stuff like that, the digital devices that we basically need. You'll be shocked. PLCs can do mathematics. Sometimes you get trick functions within the thing. In fact, anything that a computer can do, we expect that the average PLC would be able to a certain degree, be able to do lots of. Now, programs are stored in RAMs. Obviously, some basic programs they are stored in RAMs. Therefore, they need to have a backup battery, because otherwise, this. Our storage, more computer storage can be magnetic circuits and whatever. So over time, those circuits can be de-energized one way or another. So now you need to have a backup battery, CMOS backup battery. Usually it's CMOS RAM, so you have a backup battery for that. And also we have PROM modules, the programmable read-only memories. ROM, but it's programmable so that you can program it, you can write your programs into it. Now, typically there will be inputs and outputs, on average, 8. I've seen mostly 8 inputs with a minimum of 4 outputs. I've not seen 4 outputs actually. I've seen 4 outputs. I've not seen less than 4 outputs, I meant to say. So you say your input-output should be in excess of what? Of 12 for me. I'll say it to you. I haven't seen less than 8 inputs, but yeah, we normally accept that anything between 8 and 120. Beyond that, we can get expansion sockets, which are limited by the manufacturers and obviously the ability of the capabilities of the said PLC. So traditionally you'd give a number to it, but with what's happening today, you expect that to change anytime if it doesn't change already. So anyway, these programmable logic controllers, being computers themselves, they obviously to a great extent they are very compatible with our computers. Now, mostly the problems that these PLCs use, the problems that they use would be the EEPROM, because EEPROM is much more versatile and much faster. There's more reading and writing, and if there's erasure and all that, and there's programs always changing, it's most likely that you'd go for an EEPROM type rather than the UVPROM, which is not as readily erasable. Right, it is erasable, but not as readily. Obviously, it's good to know the source of things, where things started. Okay, so we need to give some a salute to Texas Instruments who started us on this path, right? But then there's so many players now. You really you have a headache just trying to to count them. They are countless. Today we've got everyone, almost everyone is doing. But I've noticed that also, like, some companies tend to have a common PLCs just branded differently. I've seen a lot of Schneiders and Eatons looking more or less like it was one product, just dressed different. You know, some would look like the same woman wearing makeup. You know, just a joke there. But anyway, if you look at our PLCs, we've said already that you would expect one of the features to be an LCD. As you can see, this one here does have an LCD, but if you look at the counterpart on the right there, the Siemens doesn't have that. So, however, it's got the added functionality of of that you would be able to. Oh, what am I doing? You would be able to. Oh, this is what. So I must remove these things each time I put them right. So that you'll be able to what? You'll be able to plug in some displays, even if it doesn't have its own display, but you should be able to plug in some displays. That on top there is, let's not be misled, that is not a PLC, that is actually the programmer. So this is a programmer sitting next, as you can see, it's actually, thank God, it's written there, the programmer, right? So it's, the programmer is the tool you use to do the programming, all right? And then the PLC is the guy you do the program on, and then the guy that will run the processes. Right now, if we then proceed, the difference between, I want us to understand the difference between hardware and software. Hardware is the physical stuff, the stuff you can actually hold. This is hardware. This is hardware. Okay, so you go to a hardware store, you pick up things that you can pick up a computer. Computer is hardware. You can pick up a PLC. PLC is anything that you can put your hands on is hardware. All right. So now, so hardwiring. When you talk of hardwiring, we are talking about physical wiring. The physical wiring, those physical wires, that will be hard wiring. And then soft wiring is programming. These are the softwares, the programs that we write to facilitate our processes. Now, relay logic is basically, if you look at, we've got physical relays, hard relays, and then we've got what was this? We've got soft relays. Soft relays are going to be, for your program, your PLC has tried to simulate, it's basically made soft copies of almost every gadget that you have, so that now if you are supposed to have a motor, you can see a motor, not a physical motor, you can see a soft motor, a motor you can't touch. You can see a simulation of a motor rather. Right, so almost everything these days has got relay. You find that relays basically can be hard and can be soft. So when you use soft relays, okay, that will be what? That will be relay logic. When you're using those switches and whatever, that will be like relay logic. But now with ladder, what we look at, if you look at a ladder diagram, I want to take a pen. If you look at a ladder diagram, if we know a physical ladder is something like this with rungs, so that we can climb up to the top. Well, these rungs, these ladders, PLC ladders actually run down, right? You actually climb down. Okay, you use the ladder to climb up and down. So our PLCs, yes, we will climb up when you get to the end statement. But what I want to emphasize there is that when we program PLCs using ladder logic, we would put we'll put elements on the what? On the in lines, all right, in complete lines. This is more, it represents power lines, and this represents power connections from left to right. All right, so now if I had an element here, I would put my elements all the way up to the what? Up to the last, and the outputs will be the ones on the what? On the rightmost. Our outputs will be on the rightmost. Therefore, after I'm done with that run, I have to come down and write on that program. So when the PLC comes to scan the program, it scans from what? Top left all the way to the end, come to the next rung all the way to the end, and those would be our scan cycles there. Those will be our scan cycles. So because it is built up, the programming is done in a sort of ladder way. We call it ladder logic. Now, when you talk of PLCs, what are they really? PLCs are basically computers. If you look at a computer, how a computer functions, and a PLC, you will find that it's basically about inputs and outputs and the microprocessor and the supporting hardware, or supporting, yes, hardware. Okay, so you would have your field devices. Your field devices is what you would use to what the inputs, what would come into the, what is supposed to your field devices would have stuff that should supply the PLC. Your field devices should include stuff that is going to be driven by the PLC. So you have your input module for the inputs, and then those devices could be switches, could be sensors, they could be anything. Then your output module will then drive the whatever outputs that you've connected to the PLC. It could be stuff like indicator lamps. It could be stuff like contactors, for instance. It could be relays, physical relays. And then you have to you remember, we need, when you program, we need to, the computer needs to, this microprocessor responds to programs. Yes, you say it's a decision maker, but how does it make the decision? It takes those decisions as instructions that come from from the program. So that's why we have, I want to disagree with this this thinking that it's always a handheld programmer. Like I've shown with the other PLC there, I think I've shown the other PLC where the programmer was actually on the PLC itself, or if I haven't, I'm still going to show it. Now, I wouldn't want to always say that the PLC is going to what is going to always have a handheld program. All right, of course you can plug a PC or a laptop via the COM cable, can do the what, can serve as a handheld programmer. But some PLCs do have their built-in programmers. Not that it stops them from what, it stops them from having another what call this, an external programmer. No, it doesn't. So you would have obviously your RAM for backup, for the what, for the programs, and then obviously it must have a battery to keep the programs to keep the program stored even when the PC, when the what, when the processor, not the processor there, when the PLC is off, right? So the you have your CMOS RAM there. Your CMOS RAM will store those programs if the what, if the battery was to, if the PLC was to go off. Now, that being said, we need to look at these. What are these other gadgets? The PLC simulates most of our hardware. You will have you have timers, you have switches, you have conductors and relays. You have whatever you have. The PLC simulates the operation. That's why I said it makes soft copies of our hardware, so that where there is no need for physical hardware, you will have what you have, internal relays doing the job. If this was about turning on, instead of so much wiring to think, you could just have a program which is not physical, and then the program would go and instruct a particular supply, a particular output to supply, let's say your motor or whatever output you want to run. Instead of having all these other physical gadgets, you would have the program doing most of the work, playing most of the role that some hardware would have to fill in. So the PLC, through its programs, sort of reduces the need, not really the need, it reduces the amount of hardware that would otherwise be necessary. Okay, most control circuits, if you look at the traditional wiring, if you're going to have motor control, you'd have a main circuit and the control circuit. It was a lot of wiring on the main circuit, a lot of wiring on the control circuit. Most of that control element has been taken over by what? By PLCs. All right, only save for actuators and whatever, and switches and whatever other control elements that cannot be that cannot be eliminated. But otherwise, other than that, we see that if we're talking of hardware, Hey, if you talk about the hardware, we're talking about the physical wiring of these PLCs. Now, if you're going to look at the amount, this is us wiring a PLC. At the end of the day, it looks nice and neat, but internally, there's all this wiring that is unavoidable. All right. If you look, this is this is one piece that I opened up just to show you. When you see it from outside, it looks like it's just an innocent little. Inside there, it's actually such a monster. So now, if I go further, there is almost closed up. Once it's closed up, it will look so. I mean, just imagine that it's not down there. It's actually sitting up. You see a beauty only, but meanwhile there's all that spaghetti in there. All right, now what I'm trying to say is the hardware includes the wires. It includes everything that you cannot that you can lay your hands on. As long as you can hold it, that's hardware. Now the software for the soft wiring, for the software for the soft wiring. With soft wiring is all the wiring that is done by the what by the letter program. Remember, if I'm drawing letter program, it's like I'm actually wiring. It's actually like I'm wiring. There is my power lines. There is my rungs. It's like it's as if it's wired together. When you look at it, it's a picture of what of something that are wired together. Meanwhile, there's nothing wired to anything. It's just a program. So that is basically the difference then. Now, building blocks of a PLC. Obviously, you need a programmer itself. You need the what? You need the controller, and then you need what in the event that there's more processes, you would need an expansion. What an expansion unit. Right now, what is a programmer? What is this programmer? The programmer is basically what? It's basically the PC. If you're using a PC, it is the handheld programmer I spoke about earlier. It is the built-in programmer. It is what you are going to use to what to write out the instructions. Right. Normally, if it's not built in, it's obviously plug and play. Well, it's pluggable. You plug it into some slot on the controller itself, and then you do your thing. Now, as you can see, I don't know. I think I'll show this a little bit. I've got a picture of this. I'll explain what I want to say now later when I deal with that part. All right. Now, let me just take us further to the basic unit. Now, when you're talking about the basic unit, oh, I want to move this up. I'm still having a pen. Look, the basic unit is a standalone programmable controller. Okay, it would have terminal blocks for the input and the output modules. So you need to be able to wire into it and wire out. Obviously, a power socket to plug your power. In the event that alarm contacts, normally those contacts would be well maybe in the old days, but these days you can wire alarm to any of your outputs in the event if there's a need for that. And then obviously the pro module plug, and then you have what your cable. Your cable when you if you're going to program, you need your like I said, if you're using an external programmer, you would need that link would normally be what a cable. That cable must have a plug where you can plug it. Okay, obviously if you need to expand if your PLC, if there's more if your what do you call this, your operational space is much larger than the capability of one PLC, then you can expand it. Okay, so you need to have those expansion connectors, and then obviously your LEDs. Usually our PLCs, if you look at my guy here, you see how many LEDs. All these LEDs here just indicators to tell me what's going on with my inputs and my outputs. So there's actually a lot more. Anything that can make that can facilitate your PLC to communicate with you as easy as possible. Now, if you look at what we showed before, that was that was the controller. That was, no, that was the what call this? That was not the controller. That was the PLC. Right now, there is the what? There is the controller. More or less, you can see this is common. If you look at this part, it's actually common. If you look at this part here, it's actually common, very common. Okay, if you look at this part, it's actually very common because basically this is a computer. This is the basic building block of a computer. All right. So now what you have now with your if you have input physical inputs, your input module must be able to what? This is normally to be transducer type of relationships. It must be able to read your inputs and be able to what, and be able to translate them into a usable form and be able to send it to that, to your CPU. Your CPU must be able to according to the program, interpret those signals and then instruct instruct your outputs. So from your CPU there, we're supposed to be able to instruct our outputs. Okay. So also in the event of a what, of an expansion, we need to be able to expand our what, to expand our outputs. We can expand our inputs, can expand our outputs. If we want more outputs, can have an expansion socket for the inputs. If we want to have more inputs, we need to be able to have that capability to plug more inputs. If we need more outputs, we need to have that capability to plug your more outputs. So this is basically our what, our block diagram for the what, for the programmable controller. Now moving on, if you can then look at our PLC again, a reminder, these are macros. Yes, they can be expanded via what, via little cables there. Normally this is our display unit, this is our what, this is the Siemens, there is our what, there is our controller there. So nothing much, just a reminder. There is our cable, our COM cable for the what, for the Siemens. This is our COM cable there. Let me just highlight it. This is our COM cable there. There you can see where you plug into the PLC. You can see where you plug on your USB there for the what, for the PC. So this is for PC, where you use your PC as your programmer. Now moving on, I would like to let's say now, if you look at our basic unit, our PLCs, I think I've shown examples with 8 inputs. I've spoken of you've seen the Eton with the 4 outputs, the Siemens with the 6 outputs. We saw the Eton Kettler hammer there. The Kettler hammer there had what, at 8 inputs and thing, and 6 outputs as well. And then we had the Delta, which had 16 in, 16 out. So therefore they're all different, and remember they are also expandable in the event that you think. But then now when you look at the functions of the PLC, if you look at the functions of the PLC now, what's very important to note there is that the PLC has to be able to do a self-test. In the event of hardware failure, you don't want the program circulating endlessly there, being lost, being lost within itself. So to avoid that unnecessary endless loop, we have what is called a watchdog timer to do the self-test in the event of hardware failure, where such looping might occur. Scan times are supposed to stay within certain parameters. If scan times are exceeded, then the watchdog timer has to shut down the input-output modules and say no, something is wrong here. Okay, that is also part of diagnosis. Now, when you talk of scanning, I've already shown on the run there. The scanning starts from the top on the left of the ladder and sweeps through to the right, and then starts again to what, runs to the left. So it keeps sweeping. Basically, it's a zigzag process. Keeps doing that. I'm using the wrong instrument. It keeps there, comes back there. This is maybe probably I should. No, this one. Okay, that rubber. All right. Probably I should do this. Sweeps like that. Runs back. Checks the second run. Runs back. Third run. Runs back. Fourth run, until we get to the end. So obviously your scanning time will always depend on the what. Your scanning time will depend on the size of the program. The longer the program, the longer your what, your total scan time. Now, to say PLCs are the same, it won't be true, because some of the speeds, just like what was this PCs, and the PCs have got different speeds. Also, but for general purposes, really honestly, it's very difficult to see. When you see with computers, you can tell that okay, this computer is slow, the computer is fast. But with the processes that are in industry, very few programs in industry, very few operations in industry are lightning fast. So usually it's not easy to tell. It's not easy to tell some of these little character, I'll say, differences between PLCs. But on the general, most PLCs would handle most jobs reasonably well. Alright. So now when you look at the memory devices, already spoken of the RAM, we spoke of the EEPROM, we spoke of the what? The the UV EEPROM, which we don't use for PLCs, really don't use, because PLCs are usually we seldom use that, because PLCs need to, most programs are changed anytime we feel like, so we do not want something that's going to limit us in terms of that functionality. Okay, so now obviously the CMOS RAM has to be what, has to be picked up by a battery. We've already mentioned that. So now, because remember, these memories tend to be volatile, right? So data will be lost if power is to be taken away. So again, these batteries, from experience with PCs already, if you've experience with PCs, they really last a long time. They really last a long time. Safe to say between 5 and 10 years should be a reasonable time to expect them to be okay. Now I want to show just different PLCs, just to highlight what we've been saying here. There is our inputs. There is very well indicated for us. There's 8 of them. Then you can see there's 4 outputs here. So in total, 12 input output thing here. And now if you look here, this is a power supply of 230. You find the model that will say DC something. This says AC. You find a model that says DC, which should usually work with 24 volts. So that is one PLC there. If you look, there is a Siemens PLC. This one works with 24 volts. There is that cable that I was talking about. This type of cable would plug in. This type of cable here would plug in on this PLC. That USB would go to the what? Would go to the computer, the computer PC, and then this one here would go onto that slot there, onto this slot here. Okay, as you can see, the VGA. So this one uses VGA. So now let's see if you can look around this particular PLC here, you can see that okay, there are you can plug in. This is a training module. You can plug in. These are inputs are wired to this thing here, so you can plug in whatever you want here. But you've got indicators here, so 2 of our outputs are taken by those indicators there, and then we've got one red indicator, one green indicator there. We've got the emergency stop. So one of our inputs is taken by the emergency stop. Obviously, the emergency stop has to be on the input side. You'd expect some machinery control here. If you see emergency stop, you expect that this is going to be this is set up to run some machine. Right, then you see here that these are what? These are other inputs there. Inputs 1, 2, 3 there. Those are what? Those are push buttons. And then you can see also here that we've got other inputs here. These are sensors there. These are our sensors. This here is our limit sensor. Those are capacitive and inductive sensors there. So now, this is basically what you do. But this is Siemens. Remember that it's got what? It's got 6 outputs, and this side is the input side. So you can see there's so many inputs there. That includes the power. Some of these cables here for power, but there's about 8 inputs there. On the other side there's about what called 6 outputs. Alright, so basically let's look at a different one. There is a delta. If you look at the delta, you can see that is got all these inputs, x0 to x7, then x10 to x17. So 0 to 7, 10 to 17 is 8 apiece, so that will be 16 inputs in total. As you can see, it also has there the same number of outputs, 4 per. This is a common for each, and each common goes with what? With 4 of them. There you see y0 to y3, you see y4 to y7, y10 to y12, and y14 to y17. That in total, you can see it's also just like it was 0 to 7 here, 10 to 17, it's also 0 to 7 here, 10 to 17. So it's also 16 inputs. As you can see, the input there, the input to the PLC itself is what? Is 230 volts. So this is a 230 volt gadget, but then it does have an output on the input side to drive it with 24 volts. So you can see it does itself have, it reduces the power itself. This is, once you plug in your 240 volts there, you get from this output here to what called this 24 volts coming out. Alright, so now it also has the ability of, you select whether you want to sync or source. So this one has ability to sync and source. Later, when there's a need to discuss syncing and sourcing, right now I'm introducing the PLC. Syncing is when the PLC becomes the source of power. What call this sourcing? No, not syncing. Sourcing. What I explained was sourcing. Sourcing is when the PLC is going to play source, all right, and then syncing is when the PLC is going to play ground, when it's going to what sync the power onto it. But we'll discuss that more in detail when the need arises. For now, I'm just introducing the basic concept of PLCs. We are not programming yet, we're not doing all those things, we're not doing the wiring yet. So when you do the wiring, we'll deal more with the other stuff. Now, when you look at this one here, this is the one that I saw a long time ago. I liked it. I was not really that much into PLCs at that point. I knew them, but I hadn't really worked with them much. So I made this one. I was like, wow, different one. Let me take a picture. I might need this today. I need this to show you as students. There you see the power. It's 100 and what? 115. Okay, so you can see how many inputs. It's got 8 inputs, 0 to 7. How many outputs? It's got 6 outputs, 0 to 5. There is you can connect your what? There's a computer link there. You can connect your you can see it looks VGA. It's shaped VGA almost. So now there is your the programmer there. You can program your what call this, and plug in your programmer there. Right now, if you look at the outputs and the inputs, if you go up, you can see that there is the 8 inputs. Alright, so it's actually using push patterns. In this case, it's already pre-wired. Your 8 inputs are already indicated there, and then there is your what? Your 4 outputs. These are just indicators. These are actuators. These are switches, but these are what? Indicators, just LEDs to indicate for you when you when you should expect a certain output to be high or to be activated. So now those are the PLCs. Let's look at what else. What other jargon? When you talk about this, remember when it comes to you're talking about computer. So that computer jargon, that computer language, expect it here. So we come to discuss again what you call this, your programmable read-only memories, which is your EEPROM, being low power, fast, and whatever, retentive upon loss of power. That's having a what? EEPROMs do not require a battery because what? Because they've got they tend to be retentive. Yeah. So now, but your RAM needs a what? Needs a backup battery. All right. Now, if you come and look at this, the pills that I've been showing you, I showed the Kettler hammer with 115 volts input. Now I showed the what? The Eaton with the Muller, Eaton Muller with the 230 volts. Then even though we didn't see it, the Siemens uses a 24 volt supply. Now, but remember that our memory modules and the CPU itself, they're actually digital devices. So they operate at what? They operate with 5 volts. So some of these spurious voltages and whatever spikes on power lines and interference that is picked up generally in the wiring session, there's a lot of magnetic fields being created there. Therefore, there can be what call this noise. So we need to have your input and output modules must be able to what? Must be able to stifle any such disturbances. So this electrical noise must be what? Must not enter. They must be. How do we achieve this? We achieve this through what? Optical isolation. Either using what? Examples is use of optoelectronics. You could have your optical. Let's say your. Remember, there's LEDs. Then there's what? There's LEDs, there's what goes this LTRs and whatever those things. But when it comes to what? When it comes to photodiodes and phototransistors, we could use those to what? To do the isolation. All right. So you can signals coming from the one to isolate. If 2 circuits are supposed to be isolated electrical, what call this? If they're supposed to isolate it through optoelectronics, this optical isolation, what would happen is the one circuit will connect with the other circuit through that LED phototransistor, what call this link up without being physically connected together. But then obviously that's not difficult to understand. I would have wanted to first remove those they tend to disturb me. Now if I come and say, where do we use PLCs? Everywhere. For me, a simple answer is everywhere. These days, there's nowhere where we don't see PLCs. In the house, we have PLCs. All the automation, if you want your garden sprinklers to work, as long as it's automated, if you want them to work automatically, if you want your garage door, your garage gate, your garage doors, and your what call this, your sliding gates and whatever, all those things can be what? Can be. So in industry, it's everywhere. Electrical engineering, civil engineering. I do not want to put a limit to it. Farming, for that matter. I mean, all those crushing devices. They can be. I'm talking about the hospitality. You can talk about microwaves, for instance. Okay, anything, industrial microwaves, industrial washing machines. So I do not think of any industry that does not use these PLCs these days. All right. And then when it comes to terminology, I really suggest that you acquaint with as many PLC terms, not PLC, computer terms as possible. Most of them are actually very, very relevant in this PLC industry. If you talk of addresses, for instance, in computers, talk about what addresses for your memory locations and stuff like that. You talk about your bits, your ones and zeros, your data bits, your ones and zeros, your bytes and everything. You compare. You need to be able to you need to have a compare function so that you are able to what to compare programs that are stored in different places, and then obviously you need counters. You need what call this? You need counters. You need timers. You need. There's a lot. I mean, anything that you can think of that is relevant for the PC. Diagnostics. You need to be able to check what call this. In the event of troubleshooting, you need to be able to run diagnostics to see that everything is what your programs and your field devices are not in conflict. So there's a lot when it comes to this. I mean, if you talk of elements, I was already referring to elements when I was doing the ranks. I was calling the input, my input elements, my output elements. So there's the end statement. I said, okay, the PLC must run until it sees an end statement. There is a lot. I mean, dash coils, logic elements, messages. This is really computer jargon. I wouldn't really want to waste my time, because what I want to, however, I will mention them as we go, as and when we need them, because there's so many of them. I wouldn't expect people to claim them, but the more you use them, the more they'll start being part of your language. Inputs and outputs. You know our inputs. Normally, I for input, the first letter of input is I, so we normally use our I as our inputs. But also, you saw the other one, the delta, that was using the X. And for my exercises, I'll be using the what? I'll be using the X's as our inputs for the course that we're dealing with. I'm using this gentleman's guide, Mr. Blinet. I'm using that gentleman. Remember, I said I'm doing this primarily for the NCS course, so he's using X's. I'm also going to do that, but nothing stops me from using I's from time to time, because there's nothing, I wouldn't have done anything wrong. Now, for our outputs, normally it can be O, it can be Y, it can be what call this Q's. So normally any of those would do. So I would really expect people to I wouldn't actually, let me rather say, I wouldn't expect people to claim all these things now. But as we go through the list, as we program, these terms will keep coming back to us. They'll keep coming back to haunt us. But the more we use them, the more. I mean, we know so much of our of these tongues that are not our mother tongues. Why? Because we kept hearing it so much and we kept using it so much. Now today, it's our second languages. So yeah, let's make our computer, our PLC terminology also our extra language. Now let's look at these symbols. There is more, but these are the basic symbols that you basically will not will see with any letter programming. All right. So now that there is a normally open contact. That there, what does that mean? I'll demonstrate normally open and normally closed when you are doing the programming. But you should understand normally open. It means it's broken until activated. Okay. And then normally closed, it means it's closed until activated. When you activate, you break it. Yeah. Then connections, any line, just like in normal diagrams, a line means a connection. So any line between two elements will mean one connection. Our output coils In this case, we're going to use Y's for outputs. Remember, we could use Q's. Remember, we should. So it depends on the PLC that you're actually dealing with. This PLC here uses Q's. The other PLC here, the Delta, uses Y's. The Siemens one also uses the Q's. So I can double check there. I know it. I've been using it all this time. It uses Q's. So now that Katlaheimer uses, if I remember correctly, it uses Y's. But let me. I don't know. The Katlaheimer. The X's and Y's, so it uses X's and Y's, right? So this one is not a Katlaheimer. I forgot that. Okay, this one is not a Katlaheimer. So the Katlaheimer, but I'm seeing from the programmer here, there's X's and Y's. All right. So that one's a different product. So it's actually not even working. So I'm not worried about it. Now, if you look at the timer, then the timer uses T's. There is some relays that you can wire physically. What do? You really take a wire and you go and plug it on a relay and you screw it on. That is what you call an external relay. That is not part of the later program, obviously. Within the program, there is what simulates those relays, and we call that what? We call that internal relays. And those internal relays are what? There's internal relay, the output, the coil. Then there's the internal relay, the input, the contact. So now that is the contact. That is the relay, normally open contact. It would be nice if they also shown a normally closed contact for the relay. This is normally open, but you could have normally closed and normally closed to be. Now let me rather leave that there and rather come here and say we could have an internal relay and it's normally closed, in which case that relay will be is internal, so it's still, we use the letter R, sometimes we use M, okay? So now it will have that closed marking there, okay? It will have those steps to say it's closed. So that would be an additional one, but there is an internal relay, the coil, this is the coil, those are an output coil, that's a timer coil. Every time we have a coil, some you see some PLCs would actually use a cycle, right? They would use a cycle as the output coil. So others would use a bracket, but it's whatever. Right now, we'll see them as we work with them. So as and when we encounter them, we'll deal with them. A one-shot contact, that arrow there says it's a one-shot. So once you activate it, you will need to find you need to send a signal to it again to deactivate. Right? Once it activates, it stays on until you deactivate it. Now the end statement is simply saying our program is done here. So let's run back to the top. Let's look at an example of a practical application. These will basically be examples, basic examples. We'll go to the programming a little bit later. So now let's take this here and then says these are examples. Draw label data diagrams for the following logic gates. Do not include latching circuits in your diagrams. Now, an AND function using two inputs, as you can see, this is normally open, meaning that there is no power to this coil under normal circumstances. Alright, so now when you activate that, it's not enough because the other one will still, this part will still be broken. So when you activate both, so X0 and X1 are both closed, meaning X0 and X1 need to be activated if you're going to get power. So if I were to put if I were to put what you call a truth table here, X0 and X1, and that will be Y0, what would happen is they can both be open, one open, the other open, both closed. Then you will see that if you don't activate any of them, you cannot have power. If you activate only the one and not the other, that will be broken. If you activate that one and not this one will be broken, so you cannot have power. Only when you activate both, do you have power. So as you can see, that is our AND gate. Right, so now if you look at the next one there, you will see that, oh, what they do. Right, let me just go back down because this looks like it's going to take a little while. Oh. Okay, we're here, weren't we? Right, now if you look at the next one there, they say the NAND function. If I, let's again use our truth table to see if this is true and y is 0. If I do not activate any of them, these circuits remain closed, and this will have power. If I activate the second one and not the first will still be closed, so we'll still have power. If I activate the first one and not the second will still allow power through. Only if I activate both, because in this case here I break that and I break that, there's no way power will go through. As you can see, that is the truth table of the what? Of the AND. With that, we come to the end of our first session. We'll meet again when you start with the programming. Hope that was interesting. I know these terms you can really start to swallow your tongue. It can really get very, I don't know, you can start, there's also something called talking too much. You can end up talking too much and really swallowing all the meaning and interest for that matter. So I hope we didn't fall in that trap. I hope we'll still be able to enjoy the programming going forward. Go through this, go through the notes on your own. Remember, you can freeze the notes anytime and read them at your own pace. And then let's meet when you do the programming. With that, let's get ready to rumble.